New York City is in a fight it did not know it was losing. Scientists have now confirmed the city is subsiding, sinking, and in some places, the rate is accelerating to a level that was once purely theoretical. This isn't a problem for the next century. It is a crisis measured in millimeters per year, happening right now, and it exposes the city to a threat that no wall can hold back. The ocean is rising, the land is falling, the gap is closing far faster than anyone was prepared for. What you are about to see is not a guess. It is a measurement captured from space. Let me know in the comments below what part of this city's future worries you the most. We expose inconvenient truths like this every single week. But here's the problem. A huge number of you who watch this, who value this, forget to subscribe. Don't let that be you. If this kind of deep analysis is important, hitting that subscribe button is just as crucial. It's an emergency alert for your feed. Let's begin. The end of New York City will not come from a single cataclysmic event. It will come as a slow, relentless advance of water, an invasion measured in inches, a battle fought at the tide line. The official data is unambiguous. At the Battery, the historic southern tip of Manhattan, the sea has already risen by about 9 inches since 1950. That's a documented fact, recorded day after day by tide gauges operated by the National Oceanic and Atmospheric Administration. That one number, 9 inches, is enough to rewrite the city's entire relationship with the ocean. It means every storm surge starts from a higher platform. Every high tide pushes further inland. Every coastal flood is more severe than it would have been just a generation ago. But that is only half the story. It is the part we have known about for decades, the part we have been told to worry about. The hidden half of the equation is the ground itself. The solid earth beneath 8 million people's feet. For an untold amount of time, we assumed it was stable, a fixed variable in a changing world. That assumption was wrong. New York City is sinking. On average, the 5 boroughs are subsiding at a rate of 1 to 2 millimeters per year. It sounds small, insignificant, the thickness of a coin, but that is the average. And averages lie. They hide the extremes, the hotspots, the places where the city is sinking much, much faster. This is not a single problem. It is 2 separate forces working in perfect, catastrophic harmony. One is ancient, a ghost of the last ice age. The other is modern, a direct consequence of the city's own ambition, a price being paid for the skyline itself. And together, they create a double threat. Sea level rise pushing the water up, and subsidence pulling the land down. It is a geological pincer movement, and New York City is caught directly in the middle. The question is no longer if the city will flood more often. The question is, how much of it will be permanently lost? The idea that a city could be too heavy for the ground it sits on sounds like science fiction. It is not. In May of 2023, a study was published in the journal Earth's Future that for the first time put a number on the sheer mass of New York. The lead author, a research geophysicist for the U.S. Geological Survey named Tom Parsons, calculated the cumulative weight of the city's 1,084,954 buildings. The result was a figure so large it borders on the incomprehensible, 1.7 trillion pounds. That is 764 billion kilograms, the equivalent of 140 million adult elephants stacked on top of an island, a concentration of mass unlike almost anywhere else on the planet. That weight presses down. It does not matter if the building is a 100-story skyscraper or a 3-story brownstone. The mass is relentless. It compresses the earth beneath it, squeezing out water and compacting the layers of sediment like a giant hydraulic press. This is not a uniform process. It is a tale of 2 cities, defined by the rock beneath your feet. Most of Midtown and Lower Manhattan is built on a foundation of metamorphic bedrock called Manhattan schist. It is ancient, hard, and incredibly strong. It barely yields under the weight of the skyscrapers that define the city. It is the reason Manhattan could be built so high in the first place. But much of the rest of the city tells a different story. Large parts of Brooklyn, Queens, and the Bronx are built not on bedrock, but on softer ground. A complex mix of clay, sand, and silt deposits left behind by retreating glaciers. This ground is more porous, more compressible. It is this ground that is deforming under the 1.7 trillion pound load. As Tom Parsons explained, the weight pushes down on the ground, and that causes the minerals and the soil to deform and to compact. The iconic structures of Manhattan get the attention. But it is the lower-rise neighborhoods of the outer boroughs, built on weaker foundations, that are feeling the pressure most intensely. The city's greatest triumph, its iconic density, has become an accomplice in its own slow submersion. Every new tower, every condo, every office building adds to the load. Millimeter by millimeter, the weight of ambition is pushing the city down. We've talked about the weight of the buildings, and soon we'll talk about the Ice Age. But of these two immense forces, which do you believe poses the real long-term threat? The one we built, or the one we inherited? Let me know in the comments. And yet, the weight of the buildings is only the more recent, more human-sized part of the problem. A second, far older process is at work, one that began long before New York City was even a thought. A geological echo of a world that no longer exists. 24,000 years ago, this region was buried under the Laurentide ice sheet, a colossal glacier miles thick that covered much of North America. Its weight was so immense that it physically pressed the Earth's crust down into the supple mantle below. But like a person sitting on a mattress, the depression in the center caused the edges to bulge upward. The land where New York City now sits was part of this forebulge. It was uplifted by the immense pressure happening hundreds of miles to the north. Then, around 11,000 years ago, the ice began to melt. The great weight was lifted. The land to the north, once crushed by the glacier, started to rebound. It is still rising today, but for every action, there is an equal and opposite reaction. As the north rebounds, the peripheral forebulge that was once pushed up is now slowly, inexorably, sinking back down. This process is called Glacial Isostatic Adjustment, GIA. It is a planetary scale rebalancing that is still unfolding more than 10 millennia after the ice disappeared. It is the deep, foundational reason that the entire U.S. Atlantic coast is naturally subsiding, a geological debt coming due. New York City was built on land that was always destined to sink. The city's inhabitants just never knew it. They built a metropolis on a slowly deflating geological cushion. For centuries, the process was too slow to notice, too subtle to matter. But now, combined with the crushing weight of the city itself and the accelerating rise of the oceans, this ancient geological process has become an active and present danger, a ghost from the Ice Age, working in concert with the modern pressures of urbanization to pull the city down toward the sea. This isn't a theory. It is the unassailable geological context for the entire eastern seaboard. The ground is not static. It never was. Until recently, our understanding of this process was based on models and geological history. Scientists like Tom Parsons could calculate the weight and predict the effect. They could study the past to understand the present, but they could not see the sinking in real time. They were measuring the cause, not directly observing the effect. That has now changed. A new technology has given us the ability to watch the city sink from hundreds of miles up in space, with a precision that is almost unbelievable. If you find this level of detail fascinating, it will absolutely shock someone you know. Do us a favor and hit the like button. It tells the algorithm that this is a story worth sharing. And if you know someone who lives on the coast, share this video with them. They need to see this. The technology is called Interferometric Synthetic Aperture Radar, InSAR. It is a method of using satellites to detect tiny changes on the Earth's surface over time. NASA and other space agencies have satellites that bounce radar signals off the ground and record the echo. By comparing the radar images from two different passes over the same location, scientists can create a map called an interferogram that reveals ground deformation down to the millimeter. It is a technique so sensitive it can detect the ground swelling over a magma chamber before a volcanic eruption, or the subsidence of land from groundwater extraction, or the slow, steady sinking of a major metropolitan area. In January of 2024, a team of scientists led by Meng Wei, a postdoctoral fellow at the University of Rhode Island, published a landmark study in the journal Science Advances. They used a decade's worth of InSAR satellite data, collected between 2007 and 2020, to create the most detailed map of land subsidence ever produced for the U.S. Atlantic coast. They were no longer modeling or predicting. They were measuring. What they found was unnerving. Their data confirmed the citywide average sinking rate of 1 to 2 millimeters per year. The models were correct, but the satellite's unblinking eye revealed something the models could not: specific, localized hotspots of extreme subsidence, pockets of the city that are sinking far faster than the average, places where the ground is dropping at rates of up to 5 millimeters per year, and in some cases, even more. 4 to 5 times faster than the rest of the city. Suddenly, the problem was no longer abstract. It had addresses. One of the most significant hotspots is LaGuardia Airport. Built on artificial fill in Queens, on the edge of Flushing Bay, its runways are subsiding at a rate exceeding 3.7 millimeters per year. An airport, a piece of critical national infrastructure, is sinking into the soft, marshy ground it was built upon. Not far from there, another hotspot, Arthur Ashe Stadium, home of the U.S. Open. The massive concrete and steel structure, weighing thousands of tons, is also built on the soft soils of Flushing Meadows, and it is sinking at a comparable rate. Other areas of concern flagged by the data include Coney Island in Brooklyn and large swaths of land around Jamaica Bay, a low-lying area already notoriously vulnerable to flooding. The InSAR data didn't just reveal where the city was sinking, it revealed how it was sinking. The map of subsidence aligns almost perfectly with the city's geological map. The areas of stability correspond to the hard Manhattan schist. The areas of rapid sinking correspond to the soft glacial deposits and artificial fill. It was the definitive, visual proof that the city's foundation is splintered. Your risk is determined by your bedrock, or your lack of it. This is where millimeters become a catastrophe. New York City is already dealing with a documented sea level rise of about 3 millimeters per year. For most of the city, that means a relative sea level rise of 4 to 5 millimeters per year when you combine it with the average subsidence. But in the hotspots, the math becomes terrifying. As Meng Wei explained, if you have a 3 millimeter per year sea level rise rate, and you have a 5 millimeter per year land subsidence rate, you have a total of 8 millimeters of relative sea level rise, which is a huge amount. More than 1/4 of an inch, every single year. In those locations, the ocean isn't just rising, the ground is rushing down to meet it. Stephen DeHunt, a professor at the University of Rhode Island and a co-author on the study, put it bluntly. People who live in these communities need to understand that the ground is sinking and the sea is rising. In combination, these two processes are greatly increasing the risk of their homes, businesses, and municipal infrastructure being flooded. 100. The satellite data pulled the threat out of the realm of long-term climate projections and placed it squarely in the world of immediate infrastructure planning. The problem is here, it is measurable, and in the places sinking fastest, it is an emergency unfolding in slow motion. All of this data, this slow motion sinking, forces a confrontation with a memory that New York has tried to fortify itself against. The night of October 29, 2012, Hurricane Sandy. Sandy was not a particularly powerful hurricane by the time it reached the city. It was its sheer size and the freakish angle of its approach, coinciding with a full moon high tide, that created a devastating storm surge, a wall of water that funneled into New York Harbor, overwhelming seawalls and flooding vast sections of the city. The images are unforgettable. Subways, tunnels transformed into saltwater canals. Entire neighborhoods in Staten Island and Queens erased. The power grid for Lower Manhattan knocked offline, plunging the financial capital of the world into darkness. Sandy caused an estimated $19 billion in damage to New York City alone. It was a brutal lesson in the city's vulnerability. A lesson that spurred billions of dollars in coastal defense projects, from flood walls to elevated infrastructure. But here is the terrifying question that the new subsidence data forces us to ask. What would Hurricane Sandy look like if it happened today? Since 1950, the sea level at the Battery has risen 9 inches. The ground in many of the hardest hit areas has sunk further. That means a storm of the exact same intensity as Sandy would arrive on a higher launch pad, pushing a more destructive surge into a city that sits lower than it did a decade ago. The barriers built after 2012 may no longer be high enough for the conditions of 2024. Millimeters matter. They accumulate into inches, and inches are the difference between a flood that reaches the curb and one that inundates the first floor. The difference between a subway system that runs and one that drowns. The 2024 study points out that along the Atlantic coast, a population of up to 2.1 million people lives on land sinking faster than 2 millimeters a year. These are not statistics. These are communities, homes, lives that are being systematically exposed to a greater risk of inundation with each passing year. The sinking is not uniform, and neither is the danger. A resident in a midtown high-rise built on bedrock lives in a different physical reality than a family in a single-family home in the low-lying coastal areas of Queens or Brooklyn. This isn't just an issue of rising water, it's an issue of deepening inequality, where geological luck determines your exposure to a climate-driven disaster. The stable ground is, for the most part, where the most expensive real estate already sits. The softest, most vulnerable ground is often home to working-class communities and critical public infrastructure that serves the entire city. LaGuardia Airport does not just serve the wealthy. The roads and tunnels that are threatened by increased flooding near Jamaica Bay are lifelines for millions. The problem is localized, but the consequences are universal. This silent, creeping threat forces a fundamental reevaluation of what it means to live in a coastal city in the 21st century. The engineering response has been, predictably, to build higher. Gigantic post-Sandy projects like the East Side Coastal Resiliency Plan, a multi-billion-dollar effort to build a system of walls, gates, and elevated parkland to protect a stretch of lower Manhattan, is a testament to the city's determination. It is an impressive feat of engineering, a modern fortress against the sea. But here is the contradiction pivot, the flaw in the logic of fortification. You are building a wall on land that is itself sinking. You are in a race to build up faster than the ground beneath you gives way. How high does the wall need to be? The calculations made in 2015 might be obsolete by 2030. The projections for 2050 might be a wild underestimation. It is like trying to patch a hole in a bucket while the bucket itself is dissolving. I know we've mentioned it before, but with more than half our viewers being non-subscribed, it's a number we have to try and change. If you've made it this far into the details, the value is clear. Subscribing is the single click that ensures we can keep funding this level of research and analysis. It is genuinely important. Please take a second to do it. The problem runs deeper than any seawall. It challenges the very permanence of the city. For centuries, New York has been defined by its defiance of nature. A city built on a small island, expanded through landfill, reaching for the sky. It has always treated the physical world as a problem to be engineered. But this is different. This is not a river to be dammed or a shoreline to be extended. This is the very crust of the earth, responding to forces both planetary and man-made. You cannot engineer your way out of geology. Not forever. The city is now caught in an unsolvable bind. Continuing to build, especially in the vertical, hyperdense way that defines New York, adds to the load that accelerates the sinking in vulnerable areas. The very act of growth may be compounding the risk. Yet, failing to grow is not an option for a city that is the economic and cultural engine of the nation. It is a feedback loop from which there is no easy escape. What happens when a runway at a major international airport subsides to the point it is no longer safe? What happens when routine high tides begin to flood coastal neighborhoods not once a year, but once a month? What happens when the trillion-dollar insurance market decides the risk of covering properties in these sinking hotspots is no longer tenable? These are no longer distant academic questions. They are a matter of practical urgency, brought into sharp focus by the unblinking gaze of a satellite. The science is no longer in doubt. The measurements are in. Tom Parsons' team quantified the weight. Meng Wei's team mapped the descent. The NOAA tide gauge at the battery records the ocean's advance. Every piece of data points in the same direction, down. The city that never sleeps is built on ground that never stops sinking. It is a slow-motion catastrophe, a relentless subtraction of elevation that imperceptibly but unstoppably shrinks the margin of safety between a thriving metropolis and the unforgiving sea. We are not watching a prediction. We are watching a process. An invisible geological clock, ticking away beneath the streets, measuring out the city's future 1 millimeter at a time. The sound is getting louder, and it is speeding up. The final, unsettling truth is that New York is not an anomaly. It is a prototype. What is happening there? The combination of subsidence, sea level rise, and intense urban development is a preview for coastal cities all over the world. From Miami to Jakarta, from Venice to New Orleans, the same forces are at play. New York is simply where the data is newest, the measurements most precise, and the stakes most visible. The plans to build walls, to elevate homes, to retreat from the most vulnerable shorelines are all necessary. They are rational responses to an existential threat. But they are also temporary. They buy time. Time for the next study to be published, the next storm to hit, the next millimeter of land to be lost. The story of New York's sinking is not a story about the end of the world. It is a story about the end of an assumption. The assumption that the ground beneath our feet is permanent, stable, a given. It is not. The satellites have confirmed it. The city's foundations are compromised, not by a sudden disaster, but by the patient, combined forces of geology and gravity. The question New York now faces is the same one every coastal city will eventually have to answer. How do you save a place that is being pulled under by its own weight, haunted by the ghost of a long-gone glacier,